Welcome, class, to the Intro to Java Programming. In this lesson, we'll review whole numbers, rational numbers, and casting. The information given in today's lesson is by no means complete, but will give you a foundation to work from and provide some good working examples. It is up to you to continue to research uses and features of existing data types, along with discovering new data types. Starting with the whole numbers, we can use the primitive data types like byte, short, int, and long. The byte uses 1 byte and the short uses 2 bytes. The range of values are listed here. The int uses 4 bytes and will hold a value between -2 to the power of 31 to +2 to the power of 31 minus 1, or roughly between -2.1 billion and +2.1 billion. The long uses 8 bytes and will hold a very large number. Here's a code example that should help you understand. Let's go to our basics project in IntelliJ, close any open tabs. Inside the data type package, let's create a new class called number test. Let's create a test that sets the value for a byte data type. Here is the syntax for declaring and setting a byte variable. The byte data type is good for holding a single byte of data, not typically used for numbers. And this test will pass. Let's create a test for short, int, and long. Here is the syntax for declaring and setting a short. Here's the syntax for creating an int, and the syntax for creating a long. All of these tests should pass. Back in the early days of computing, storing variables in the smallest data type to save memory was very important because memory was expensive. Today, we have plenty of inexpensive memory, and using the smallest data type is no longer an issue. When looking for a data type for a whole number, you should prefer int unless you have a specific need. Let's write a test that will change the value of an int variable. Notice we started with the value 42, then on the next line it changes to 73. This test will pass. Yes, we can perform math operations on all numeric data types, and we will cover this in a future lesson. Let's take a sneak peek at a math operation. Here's a test that will divide the number 9 by 5. The result is 1.8. Time for a Coach Joe challenge question. What will be the value of the myResult integer value? Correct. The answer is 1. Anything to the right of the decimal point is truncated or removed. The value is not rounded up. Let's finish the test. This test should pass. This is a good point to talk about rational number data types. The purpose of these data types is to hold a decimal value. It is said the float will safely hold the decimal point precision for 6 to 7 positions, and the double will hold the decimal point precision to about 15 positions. Here is the syntax for declaring and setting a double variable. Notice the D after the number. The default data type for a number with a decimal point is double, so declaring D after the number is optional. In this test, we'll divide 9 by 5 and check to make sure the result is 1.8. This test should pass. I would like to point out a slight difference with the assert statement. There is another parameter called delta. As I mentioned before, both float and double will hold precision to a specific decimal position. If you test for an exact value, the test may fail on a decimal position you are not concerned with. To prevent this common issue, the assert statement will use the delta to restrict the test to a specific precision level. This test will verify the first 2 decimal positions are accurate. That means the third position is not tested. Here's a test where the D is not declared after the number. Also notice that the value has 4 positions after the decimal point, and we are only testing the first 3 positions. Even though the value in the assert statement is not an exact match with the value being tested, this test will pass. All tests against a double and float data type will need a delta parameter based on your needs for decimal precision. Here is the syntax for declaring and setting a float variable. Here is a test for the float data type. Notice how you must use an F after the number. This test will pass. When working with rational numbers, you should prefer double over float unless you have a very specific need. Let's talk more about decimal precision with the double data type. Here's a test where we divide a number by 7. We then take the result and multiply it by 7. Common sense says if you divide a number by 7 and then multiply by 7, the result is the starting number. One assert statement is testing to make sure the result is greater than the initial 1 million. Watch the test pass, but notice the system output of the actual value. The 10th decimal position has a 1. Be careful using float and double if you need to keep decimal precision accurate. On your own time, you can research numeric precision in Java and many other languages to learn more. The double will hold a currency value. Calculations against the double may produce issues with values in the far right decimal position. Many issues can be resolved with rounding. A safer solution for the precision needs of currency would be the use of the BigDecimal object. Here is a test using BigDecimal. Notice that BigDecimal starts with an uppercase letter, so it's an object or a non-primitive. The keyword new is required to create a new BigDecimal object. In this test, we create the variable with a number and with a string. Notice the system output when the test is run. It is recommended to use a string to declare the initial value for a BigDecimal. Now let's write a test using BigDecimal that will divide a number by 7 and then multiply the number by 7. Will the result be the initial number? I will not go into great detail about the code used, but here the test divides the same 1 million by 7. The result is then multiplied by 7 and tested to see if the final answer is 1 million. Indeed, the test does pass. Do some additional research on BigDecimal if interested in variables that require decimal precision. There may be a situation where you need to save a double data type into an int data type. You can cast a value to another data type. Casting is the process of assigning a value of one type to a variable of another type. Here is a test that shows this example. Notice there is a compiler error if a double is stored into an int. Let's comment this line. Notice the int in parentheses. Value double will be cast into an int data type. After the value is cast to an int, the variable value int can be assigned the value because both data types are the same. Notice the result is not rounded up. This test will pass. Here is another test that will cast a long into an int. This test will pass. Here's a good place to start when choosing a data type. If you need a variable that will be a whole number, use the int. If you need a variable that will be a rational number where precision is only a few decimal positions, use the double. If you need a variable to hold currency or other rational number where precision is very important, use the BigDecimal object. Other numeric data types could be used if you have a specific need. Here's a review of the code that we wrote for the number test class. You should now have an understanding of the data types used for whole and rational numbers. BigDecimal is an option if decimal precision is a concern. Casting is a way to convert one data type to another. Many data types were discussed, and some may need additional research. In the next lesson, we'll discuss data types for dates. Your optional homework assignment is to create a unit test that will cast a double into a float data type, and another unit test that will cast an int into a short data type. Remember, future senior developers, make it work, prove it works, then make it better. Ready? Break!